So this session is on the 21 centimeter astronomy. We have about 15 or 16 minutes per speaker. So I will give a 10-minute warning because another 4 or 5 minutes to speak for the speaker. And the next speaker can set up during answering the questions. The first speaker is Rennan Barkana from Tel Aviv.
Okay, thank you. Nice to be back in CITA. I want to briefly tell you about some recent results on the astrophysical analysis of 21 centimeter experiment. And I'll try to be very brief because I decided I also want to tell you very briefly at the end about a completely different topic just to make things more lively. Okay, well, let's talk about 21 centimeters. So what am I talking about? As we all, you probably know, people are gearing up for a whole bunch of first generation of 21 centimeter experiments to measure, at least statistically, the 21 centimeter emission and through it the ionization distribution during cosmic reionization. Now the question is, how are we going to simulate it? So there's a lot of work, there's been a lot of work in the field, and we can say, at least to some rough order of approximation, that we now have some idea of, for a given galaxy population, what kind of 21 centimeter map, or ionization map, from the ionizing sources, and what kind of 21 centimeter map do you get. For example, from simulations, and we can discuss this, there's a lot of limitations to simulations, but at least approximately we know how to go from galaxies to at least a large-scale 21 centimeter mapping. However, observations will give us the opposite problem, the inverse problem. We're going to observe some kind of 21 centimeter map, and actually only statistically, not a direct map. And then we'll want to somehow invert this and go back to learn something about the galaxies and have some kind of uncertainties in the parameters of galaxies. So how do we invert this problem? How do we kind of plug in an observed map into a simulation? So I think the best way is to have some kind of semi-analytical model that is flexible, that can predict the 21 centimeter power spectrum, for example, the main statistic people are focusing on. So you can predict the 21 centimeter power spectrum as a function of your various input parameters for the galaxies that are presumably the ionizing sources. And then you can actually do a free fit and get results out from fitting the data. So here's an example of a model that I made, a kind of analytical model for the power spectrum compared to the simulation by one of the groups. So this shows the power spectrum at different times. So this is a typical fluctuation level in millikelvin in the brightness temperature and various scales, or various wave numbers. So this is early in reionization, 20%, and going up in reionization. So this is just showing how the model basically captures the quality of the results from the simulation, also semi-quantitative, you could say, although currently to the degree that the different simulations agree with each other, there's still a fair bit of uncertainty in the power spectrum from the simulations themselves. But you can see that early in reionization you have a characteristic shape from density fluctuation. Later on you have the large-scale bump, which is coming from the large A2 bubbles, the ionization distribution. Okay, so the model is reasonable enough, agrees reasonably with simulation, so we can use it to fit the data. So this is an example of a result of a projection of how well can we do if everything goes really well, just taking the expected noise from the data. So this is for the 1-year NWA experiment, but there are other experiments that are competing pretty closely with NWA for the expected sensitivity. So this is generally for the first generation experiment. And this is a result that goes as follows. So in the model, it's a simple model which has 2 free parameters at each redshift. The idea is to have a model that's based on galaxy formation, but not to assume too much that we know the properties of these very early galaxies, to allow some flexibility. So in the model, at each redshift there's a minimum circle velocity, or effectively a minimum halo mass for galaxies, which is a free parameter, and then the other free parameter is the overall ionization efficiency of that variant in galaxies. Now, just look at the top curves here, which are a 6-parameter model. So I don't want to assume that these galaxy parameters are fixed with redshift, but allow them to vary fairly freely with redshift. And that gives a 6-parameter model and gives these projected uncertainties. So This is one example. So it shows the projected error from a full chi-square fitting to the data at the various redshifts that we expect. Here I'm showing the relative expected error in the mean mass of payloads that host ionizing sources as a function of the reionization E5. So this is the ionized fraction in the universe. So here you see that even when you have 6 parameters, when you allow freedom, so down here is a less flexible model, but even with the most freedom, you get very accurate to within a few % accuracy in the mass of payloads of ionizing sources, at least during the heart of reionization, like the 2/3, when about 2/3 of the universe is ionized. And this is because here and this assumes that reionization occurs at fairly low redshift, so that's an optimistic case where the observational noise is low, and then you can see that you can measure the large-scale bump from ionization and get the typical mass of ionizing sources. Even if that mass is very small, you get it out of the reionization statistics. Now, down here is not the relative, but the absolute error, expected error in the ionization fraction at a given time. So you get you expect about 1% absolute error, which means a pretty good measurement of the how this reionization history throughout reionization, and at the very end of reionization, you expect a very clean detection of the very end of reionization when the power spectrum suddenly drops because the last neutral gas is disappearing from the IGM. So this is just a summary of some results. Now that we move on, when we talk about this going from maps back to galaxies, we don't look only at the power spectrum, which most people are focusing on. We also want to be more flexible to think of other statistics, other independent analysis that can give us the same result, hopefully, and maybe give us more information in the power spectrum as well, because the ionization field is non-Gaussian, so it's not just all about the power spectrum. The one statistic that a number of people have looked at is the 21 centimeter PDF, which simply says that you divide your field, your 3D box, into small pixels, and then just plot the histogram of values of how many pixels emit at various brightness temperatures. So here's one result. We've measured this PDF, the evolution of this PDF in simulations by the simulations are from the Ilya group, another one of the groups. Of course, at CITA we have Whaley Penn and so on, doing very nice large-scale simulations of reionization. So this shows how the PDF evolves. So this is the PDF. So this is starting out reionization and going all the way to the end. So very early in reionization, the PDF is basically a Gaussian because everything is neutral and you just have Gaussian density fluctuations. And if you go to the very end of reionization, basically everything is a delta function at 0. Basically all the pixels are fully ionized. However, during the middle of reionization, you have an interesting shape of the PDF. So there are some neutral regions with density fluctuations. There are some fully ionized pixels. And then there are some pixels that are partially filled by H2 regions and give you an interesting PDF shape. So this is an example of a projected result from chi-square fitting to the data. Again, this is the MWA, but this is more optimistic. Let's go with 4-year data, the ultimate data set. Now, this is a very optimistic case. It's actually pretty hard to measure the PDF under large noise. So this assumes that we can trust the PDF shape from the simulations. Although we now run this in other simulations, and we find that the PDF shape is reasonably independent of the precise inputs of the simulation as a function. It depends mainly on the reionization history, and so the cosmic ionized fraction. But if you assume that you can take the PDF shape from the simulation and just fit it to the data without trying to measure it from the data, then you get these results. So these are two different pixel sizes that you try to develop to divide up the same observational field. So it turns out that it's actually, so what I'm showing here is the measured versus real. So this is the input ionization fraction, cosmic ionization fraction, and this is the output that comes from the fitting. So you can see that it's better to take larger pixels because in these experiments, if you go for high resolution, you lose a lot of sensitivity. And here actually the sensitivity, getting low noise is more important. But you can get a good measurement of the reionization history independently of the power spectrum. In principle, if everything works well. We can go beyond this, and here's one idea that we developed with Avi Loeb. It's called the difference PDF, essentially a 2-point PDF, which says that you take pixel pairs at a given separation, at a fixed separation, take all such pairs and look at the histogram of temperature differences in emission level between the two pixels. So this is a kind of statistic that it's like a combination of PDF and power spectrum and a little bit more. So it has power spectrum in it because you're looking at pixel pairs, so it depends on the correlation between pairs at a given distance. And you can show that one advantage, for example, compared to the power spectrum, is that if you can really measure the different PDFs, you can get out the ionization correlation function essentially independently from the density, while in the power spectrum, the density and ionization fluctuations are all mixed together. This is a result from work with Luskevich, Caltech graduate student. We've measured in the same simulation the different CDF. So this is the early ionization. So again, it's a histogram of differences among pixel pairs. If the pairs are separated by a large distance and they're uncorrelated, and you get some basically half Gaussian. But then so each of these, each color the distance goes down by a factor of 2. If you get to quite close pairs and they're highly correlated, and then the PDF drops and it rises to 0. So if they're highly correlated, the difference between them tends to be 0. And if you can observe when the PDF drops from its uncorrelated form to highly correlated, that gives you a measurement of all the correlations that are going on here. So this redshift would be density correlations. But later on in ionization, the same kind of effect of the PDF is different because of the ionization bubbles. But again, it drops at some, so this is 4 megaparsec, 8 megaparsec. At around the 10 megaparsec level, the PDF drops off, and that will be a way to measure the ionization correlations later reionization. Okay, so that's a quick run for some 20 centimeter analysis. And now I want to very briefly, in a few slides, talk about a completely different issue, just to be thought-provoking. So a different topic, which is large Einstein radii. This is a problem for the lambda CDM model. So this is a problem that various people, I didn't put here all the references. A lot of people have commented this over recent years, that the density profiles that people measure for galaxy clusters primarily through lensing seem perhaps in conflict with the predicted profiles from numerical simulations, and often this is expressed in terms of a concentration parameter of a fitted and a W profile. So with Tom Broadhurst, we tried to highlight this issue and express it in terms of Einstein radii, because Einstein radii is something that you measure almost directly from the observations, and you can measure it similarly from simulations to try to compare directly apples and apples. So this is one example of Oval 1689. So we have many clusters now, or a growing, not so many, but a growing number of clusters, which are very well measured with both strong and weak lensing. So we took 4 particular clusters that are very well measured. So their masses, their viral or M200 masses are around 10 to the 15, so massive. Einstein radii between 30 and 50 arcseconds. And these are lens and source redshift. So the Einstein radii are defined for a particular source redshift. Now, there are a lot of groups that have done a lot of work with simulation that allows us now to compare essentially directly the simulation result to the observation. So Neto et al. Had a large sample of halos that are very well resolved, large massive halos, and they analyzed them. And then Hanawi et al. Had a slightly smaller sample, but still a very nice sample of cluster halos. But Hanawi et al. Looked very specifically at the relation between the 3D mass distribution and the projected 2D distribution. So through Hanawi et al., through their results, we can statistically convert and compare quite directly the 2D mass distributions of simulation and observation. So how do we do this? So we want to, so for the reason we have an estimate of the virial mass, or M200, of the cluster halo. Although here it's a little bit, it depends a little bit. Of course, in the simulation people use a 3D definition, and in the observations you can only do it through projected mass. However, this, so I will show you in a minute the result which is less sensitive to the definition of mass. The more important issue is Einstein radius, and I want to emphasize when I talk about Einstein radius, I'm not assuming in any way spherical or axial symmetry. Einstein radius is just a definition. So you have, in general, you either in the simulation or in the observation, you have the full 2D projected mass distribution, and then you can define an effective Einstein radius, which sort of summarizes, gives you one number that summarizes the distribution, even if it's not spherical. But the Einstein radius itself, the definition is a circular radius in which the mean projected density equals the critical density. The critical density is this combination of observer, lens, and source distances. Okay, so the Einstein radius is an effective definition that you can define in the same way in the simulation and observation. In both cases, you have a full 2D mass distribution, and you don't assume symmetry. So this is the result from the paper with Tom for these 4 clusters, where you see the predicted Einstein radius and the observed one in red. We took the distribution based on the simulations of Neto et al. And Hanami et al. The predicted distribution, including the scatter of halo properties from the simulation, and you find that the probability of finding such high observed values, which are typically about twice higher Einstein radii than predicted for halos of the same real mass, the probability is usually 1 to a few percent, the probability of finding such high Einstein radii. So we said that with each cluster, you have roughly 2 sigma problem in terms of the scatter probability. However, these are 4 independent clusters, so together statistically it's about a 4 sigma complex. Now, admittedly, this wasn't totally satisfactory, because although in the predicted result, we're including lensing bias, assuming that your cluster is biased by lensing strength. However, these 4 clusters, admittedly, they were not selected in any clear way, so it's not clear that the selection is correct. But now I want to show a more recent result. So here the first author of Dietring is a grad student at Tel Aviv University. So here we have, I think, a much cleaner result in the sense that we took the massive cluster survey. So we took from it a sample of high redshift, so all the redshift above half clusters in a particular part of the sky, X-ray selected. So it's not selected by lensing bias, and it's a clearly selected sample. So we have 12 clusters, which have, all of them now have very good strong lensing data, but this is just strong lensing. So just the Einstein radii are measured fairly directly. And then we plot this distribution for these 12 clusters of, so this is a cumulative histogram. How many have an Einstein radius above some value? Okay, it's in yellow, so you see the median is about 28 arcsecond or so. And for the same redshift distribution and so on, and the same X-ray selection, what is the predicted distribution? It's this white line. So it's roughly a factor of 1.4 offset between the predicted and observed Einstein radius distribution. Now here we don't have viral masses, so the predicted distribution includes the halo mass function and the scatter of halo properties from simulation. Now, but however, so assuming that the halo mass function is reasonably accurate, and this doesn't depend too much on masses, because on observing the mass or on figuring out how much X-rays different clusters emit, because the white line here, the predicted line, basically includes all clusters you expect to be in that part of the sky. I mean, if you change the X-ray selection level, for example, this would affect the low Einstein radii. The large Einstein radii are all massive clusters in that part of the sky. It's hard to get more of them to get these big Einstein radii. However, this is just 12 clusters, so depending on how there are different ways to compare the distribution. Statistically, it's roughly 2 sigma conflict, although it's a more clear sample, so I think this is a better result. The much larger samples are coming, so we'll have a better idea pretty soon. And just finally, just to mention, I wouldn't suggest that we have to throw out lambda CDM if this conflict turns out to be real. So one idea is that with Avilov, we had an analytical argument that the baryons, even though they are not concentrated in the center of the cluster, still through their influence on the accretion history of dark matter, they may be able to produce this kind of an effect, because we're of course comparing to pure dark matter simulation. Now there are many groups doing cluster simulations trying to look at this, the effect of baryons on the dark matter profile. And I just say one note of caution: that simulations, the main result I would say, qualitatively, is that what you get depends crucially on how you put, on what kind of feedback you put for the baryons in the galaxies during cluster formation. So, whether you believe the result depends on how much you trust the feedback as they put it in the cluster. Thank you.
Can I ask questions like you were setting up?
Rennan, is there any advantage of using your difference in PDF versus more standard search function? would be just whatever the point is.
You mean just like bispectrum or things like that?
No. You can take difference of the values in square, but you take up 3 values, so that would be a special function, which is widely used overall.
Okay, I think it would be quite similar, yeah.
Same.
Okay, then squaring would be maybe.
It's a bit nicer because it's polynomial.
Yeah, CITA.
Okay, so I'm going to talk about, in fact, we're going to call gravity wave fossils. Okay, and this is a signature of tensor modes that might be detectable in the pre-reionization 21 centimeter structure. And so I'm one of Bailey's grad students here at CITA. Okay. So a bit of motivation. So primordial tensors, so the gravity wave power spectrum is hard to detect, right? So the current constraints from W map are less than 0.4, and then U modes will do a lot better, right? But the tensor power spectrum is really the thing that inflation makes the most specific predictions for. Right? And so in particular, it has this consistency, the simple models of inflation have this consistency relation between the slope and the amplitude of the power spectrum. Okay? And so if you can, that's the most specific test of inflation. So it would be nice if we could test that. The problem is they're so hard to detect that we probably will never. It's hard to get a measurement of anything, right? However, there's an abundance. If you go to like pre-reionization 21 centimeter gas, there's an abundance of statistical information, right? So there's most of the volume of the universe is out there, and the information hasn't been erased from small scales yet, right? So if you're just counting the number of modes, you have many more modes before reionization than you do after reionization. So if you could map this, if this was experimentally possible, how would you look for tensors if you have all this information, right? So I'm going to talk about an effect that we've come up with. Okay, so let's be in let's say it's during inflation. Okay, I'm just gonna. And so the universe is inflating. This box over here is just sort of the Hubble's volume, okay? And I'm just going to put in one tensor mode, and I'm just going to be an ordinary, everyday tensor mode generated by inflation, right? And so as inflation continues, the tensor mode gets stretched out, keeps getting stretched out, and you eventually get to this point where basically you just have a DC shear, okay, across the entire Hubble volume, right? So, the Hubble scale is much smaller than the wavelength of your tensor mode. Okay, and so you put this DC shear across the universe, okay? And so I'm just going to put a circle in the middle of my universe just for reference, right? That circle doesn't mean anything, it's just there. Okay, and now I want to say, okay, now I want to do quantum mechanics and I want to generate some scalar modes, okay? But in order for me to do quantum mechanics, I need to be in a flat universe, right? Or a conformally flat universe, right? So this Hij up here in the top metric is a bit of a problem for me. Okay, but you know this shear is DC, right? So we can just gauge that away inside the Hubble volume. Okay, so I just stretch all my coordinates by something proportional to the shear. Okay, and then this is my new metric, right? And then this is just Friedman, right? Just the normal Friedman metric. Okay, and then these things are all small and they're zero at the origin, right? They're all proportional to x. So I've gauged away my tensor mode at the origin. It's not there anymore. I can do quantum mechanics. Okay. So let's do quantum mechanics. Let's generate a whole bunch of scalar modes. Okay. So I put these scalar modes in, and inflation generates these isotropically. Okay. So I've got all these round scalar modes in here. Okay. And so my power spectrum of scalar modes can be written just as a function of k. Okay. Not as it's not a function of the direction of the thing in this gauge. Okay. However, when I go back to my other gauge, right, the one where I originally started off with, the one that we normally do cosmology in, okay, in that gauge my power spectrum is anisotropic. Okay, so you've got the isotropic bit, and then you get this anisotropic bit that has the shear, right, and this shear is not suppressed by, right, this is a DC shear, it doesn't know what the wavelength of the gravity wave. It's not suppressed by, the length of the shear isn't suppressed by any separation of scales. It's just proportional to the amplitude of the gravity wave. Okay. Now, of course, this this anisotropy is completely unobservable right now, right? So if you lived during inflation, you can't say, oh, the power spectrum is anisotropic, right? Because, of course, that gravity wave is bigger than the horizon. No possible observer could possibly know about that gravity wave, right? So you can't observe an anisotropic power spectrum. But then you have to think, well, okay, so what? So now we want to move this, evolve this into the future, okay? And if we're going to evolve this into the future, which of these gauges do we know the geodesic equation in, okay? And the gauge, the geodesic equation is absolutely trivial as the top gauge, right? So this is the transverse traceless gauge. It's conformal time, right? So an object that's at rest in the top gauge just stays at rest for all of time, right? No matter what time dependencies, no matter how slow Hij changes, no matter what it does, it's just going to stay. A particle at rest in the top gauge stays at particle at rest for all of time, okay? So what we're going to do is, okay, so you've got our two gauges here, right? One where the power spectrum is isotropic, one where it's not, right? But we evolved this for 1 billion years, okay? We wait for this gravity wave to decay out, okay? And when this gravity wave decays out, these two gauges become equivalent, right? They're the same thing, right? Because all the differences are proportional to Hij, okay? But the power spectrum keeps its original form that was in our first gauge, okay? The gauge that had the tensor mode in it, where it wasn't gauged away. Okay, and so this power spectrum stays. Assuming your power spectrum is laid down like test particles, right? So I'm not considering the dynamics of the scalars right now. Okay? So if we let this gravity wave decay away, right, then all of a sudden this anisotropy in the power spectrum becomes observable, right? It's on wavelength smaller than the Hubble scale, and we can go out and measure that. Okay? So this is a small effect, right? So you're looking for this anisotropy in the power spectrum, right, patch by patch. Okay? And so you look at the anisotropy in the scalar power spectrum is proportional to your tensor perturbations at a time, right? You do patch by patch, okay? You construct some sort of estimator for Hij that goes something like the derivatives of locally, it's something like the derivatives of the scalar modes. Okay? And then you can do this patch by patch and get the spatial dependence of Hij, okay? And then you can do things like verify that Hij is transverse and traceless, make sure it really was a tensor mode, okay? And check all that, and do all those checks to make sure that you're not seeing something like lensing, okay? However, of course, this effect's minute, right? So this Hij is a small thing, right? And this is a second order effect in the initial conditions for inflation, right? But you don't need any second order dynamics, right? It's just putting the initial conditions, right? So you need many scalar modes to beat down the sample variance on how you measure this P again. Okay. So why is this effect bigger than other effects, right? So there's so I mean you could think of other ways of looking for tensor modes and scalar derivatives, right? So Donaldson and Rosso and Stebbins, who I think is probably in the audience, thought about weak lensing by gravitational waves, right? But this should all be bigger than that because tensor modes decay rapidly when they enter the horizon, right? So once the tensor mode comes from the horizon, it drops off really very quickly and decays away. But these fossils that are laid down in scalar perturbations are permanent, right? So they become observable once the gravity wave goes away. And once that gravity wave goes away, it's permanent. It's there for all time until some nonlinear evolution just wipes it out, right, in the scalar. Right? So because you're not limited to looking at one scale at a time, right? So, you don't have to, you can, right? Because there's more than one scale that these fossils should exist at. You can probe some range of scales in the tensor power spectrum. Okay? And so since you have a range of scales, you may think, oh, maybe we have a chance at anything. Okay? And then maybe test the consistency relation. Okay, so I'm going to run through some forecasts. Okay, so SKA will be, if you just go to Wikipedia and look up the science goals for SKA, right? One of the science goals is to see pre-reionization gas, right? So I mean, this isn't isn't absolutely crazy, right? So SKA has the core area is expected to have enough sensitivity. This core 800 kilometers of SKA should have enough sensitivity see this absorption feature around redshift 15 in the absorption against the C and D. Okay, and so this is the temperature as a function of redshift, right? And so you've got a pretty good signal here. There's a couple different linear models. Okay, so if you had 10 kilometer baselines, okay, so what matters is I'm neglecting noise in the measurement of the scale motion. We're just talking sample variance for now. So your resolution tells you how many scalar modes you have, right? The maximum K that you can go up to in scalar modes. How well you measure the scalar power spectrum. And so if you have 10 kilometer baselines, right? So you get a formula like this for the minimum R that you're sensitive to. If you have 10 kilometer baselines, you end up not being very competitive, right? So 7.3 is the minimum R that you can detect, right? So that's not competitive with the C&D. However, this is super strong function of Kmax, right? So there's Kmax to -3, right? So SK also has 100 kilometer baselines, 1,000 kilometer baselines. We'll never detect this signal on the SKA baselines, right? But the low frequency collecting areas is cheap, right? So you can imagine making another generation experiment that have longer baselines, get many more modes, right? And you get a factor of 10 baselines, and all of a sudden you're better than you're doing almost well, I guess you need you need a factor of 100 baselines to do better than E-modes could ever do, just by sample variance, but you're still doing it quite good. Okay? And then you ask, okay, so what about testing the consistency relationship? So this one's just order of magnitude. I haven't gone through the detailed calculation yet, right? But if R cooperated was like 0.1, okay, and you did the same survey, it looks like you need the minimum scale would have to be 40 inverse megaparsecs, right? So that's like 40 kilometer baselines-ish. Yeah. So, just to wrap things up. So what I just talked about was, it's a new effect for detecting primary low tensor modes in a large scale structure, okay? And we think this is would be a very powerful effect for measuring R with very low frequency arrays, or sort of at the redshift 15 ranges. That's sort of the range where we think that the most signal will be for pre-reionization. Okay? And it might be the only chance we have for measuring NT ever. And that will be pretty exciting. And testing that consistency relationship, right? The most specific prediction that inflation makes would be really wonderful. And so that's all I have. Any questions?
So at smaller scales, the modes go nonlinear earlier. Are you up against that?
You're not up against that until you're at like 500 kilometer baselines at redshift 15. I mean, like, you're starting to get there, right? But you're not at the point where like delta is 1. You're at the point where delta is like 0.1. You just need there to be the information not be completely erased, right? Because you're looking for an anisotropic, so it's fairly like even if you don't know the power spectrum right that well, you can still tell if the power spectrum was anisotropic. Systematic speed.
Yeah, I'm a little bit unclear how did you do quantum mechanics on inflation.
Well, I mean, I didn't do quantum mechanics on inflation. I just know that.
Well, my question would be the following. So it looks like you are doing a coupling between longer wave modes in gravitational waves, which makes its horizon earlier, to the scalar mode, which appears a bit later, right, at the Hubble scale. So what's actually the difference here between gravitational waves and just longer wave mode scalar modes, which are also kind of distorted?
Well, I mean, they would, right? But so scalar modes would give you like an overall, give you a traceable dilation, right? So that's hard to check, right? I mean, the argument is just that it doesn't require you to actually have to do the quantum mechanics, right? You just have to say, okay, well, there's this coordinate transformation you have to make in order to get to at second order, in order to get to the mode where, in order to get to the frame where you're conformally flat. Okay.
Yeah, well, my feeling is that accurate calculations in this part would be important for a convincing story to some extent. Because you essentially are talking about some mod coupling with inflation and
isn't it? So if you fix the right gauge, there's no mod coupling.
Well, in the scalar case, the mapping is from K Lagrangian to K Eulerian that, of course, is fundamental to the modification structure. What I also didn't get here is exactly how you're building in the statistics.
I'm just saying that locally in this patch, nothing can possibly know about this tensor mode, and that's all right. So
But there's, even though they're long waves, there's all sorts of interference.
I mean,
Discussing around the field.
right, but I'm just not sure.
Anyway, we'll talk about it later.
Okay. I mean, it's I think it's a simple argument in that, you know, if this tensor mode is super horizon, right, then nothing inside the horizon possibly know that tensor mode exists. Okay.
But I actually thought this was myself. I made an error, and I don't know if this is actually an issue. I thought superhorizon modes and gravity waves would be just the way to modify the quadrupole. Right, this is essentially the same argument. It doesn't work. But I think there's something else, which is the differential between the superhorizon and that which is within the horizon, which is essential to the fluid direction making model.
So for the quadrupole, right, the quadrupole of the CMB, that gravity wave mode would still be super horizon today, right? No.
Perhaps I can continue this discussion with a cup of coffee.
Sure.
And we move on to the next speaker. Let's thank you again. Talking about 21 centimeter intensity mapping.
Okay, so it's been 21 centimeter, actually at redshifts bigger than 0 point something. Must be one of the most talked about, must have one of the largest ratios of papers to observational data points, meaning infinity for most practical purposes. And we're working on making this infinite ratio infinitely smaller by actually trying to map what the universe is doing on 21 centimeters at some substantial redshifts, which actually is of cosmological interest. So we've been pushing the observational data sets on trying to see how one can push where we are. This is based on data that hopefully will appear in Nature in the near future. That's the backdrop that depends on how forward-thinking, ambitious a theorist you are in this room. The 21 centimeter universe, of course, is thought to be the endless information reservoir of what we can possibly see. You can look all the way to maybe 50 or 100. So Tekmak and Darayaga, very forward-thinking theorists here, have pointed out that there are 118 modes in the universe that you could in principle observe. So you can measure something to the square root of that accuracy. You can statistically measure things to 10⁻⁹ in some space. So obviously, if you think measure things, we just heard gravity waves, primordial non-Gaussianity, acoustic oscillations. Anything you've ever dreamt of asking, you can almost answer with this almost infinite supply of information. The only problem is that this is all very nice to think about, but is this, 1,000 years in the future, or 10 years in the future, or right around the corner? That's, I think, where one should one rein these theorists in, or should one encourage them to go even further? And that's why we've been thinking about how we go about actually measuring any of these. So, the basic, there are a couple of obstacles here. One is you've got the inverse square law, and in fact, cosmologically, get even worse, that things get very faint very rapidly. So in particular, the highest redshift 21 centimeter emission ever detected is redshift of 0.24. So going from 0.24 to 1 or to 10 or to 100 is certainly an ambitious thought, and it took people, 60 years to get to redshift 0.24. So if it's another 60 years, you get to redshift 0.5, then we're talking about very long-lived scientists to make benefit of it. But there is a somewhat conceptual change if your goal is to measure structure in the large differential density field compared to individual galaxies. For example, stars often stop becoming visible at fairly low redshifts. The highest redshift star, I have no idea what it is, but probably not very high. It's the highest redshift individually detected star. I mean, sequence star, let's say. That's not my supernova here. And yet, of course, collections of stars you can see quite far away. So same with large-scale structure. If you go to map the large-scale structure of the universe, you might not need to detect any individual galaxy. You might be able to see structures much further away, which means instead of requiring futuristic, gigantic telescopes with gigantic collecting area to collect the photons, since we don't actually need the resolution and we don't need the photons, you might get away with something much more modest, perhaps even telescopes that exist or can be built in the near future. Large-scale structure, just to put it in context, normally when Rennan shows images of gravitational lensing arcs that are an arc second, where the unit scale is arc seconds or below, and this is large-scale structure with the typical scale on the sky is a degree. Degree is the characteristic scale we're talking about. VAO is a scale of several degrees, is where the acoustic peaks are really standing. So the large-scale structure, hopefully this is my focus on over half, you can't see his name anymore, but we're talking about very large-scale structure. So resolution is not an issue. And sensitivity, again, if you care about these collections of hundreds or thousands of galaxies per pixel, that's the smallest resolution a person going up the power spectrum would generally care about. And then collecting area is not much of an issue either. So you might be able to get away with something much more modest. There's only one little hang up to this, is you say, well, why wasn't this done 50 years ago? I mean, the telescope has been around 50 years ago, and then there was no hydrogen out there. I think the conceptual issue people haven't quite been able to overcome is people didn't make maps. Okay, so Haslam in the 70s made a beautiful map of the galaxy with the kind of telescopes that we are proposing of building. And instead of seeing a nice three-dimensional 21 nanometer map, which he should have seen, he saw a very bright single-point emission from our galaxy. And the signal is about a factor of 100 or up to 1,000 brighter than the 21 centimeter signal. Okay, so if you look at the superimposed on the 1% in a dark little spot, there's a 1% variation below the structure, which is what the thing you want to see from the previous map. And that is a practical issue what makes this thing slightly more challenging, and why Haslam in this little map did not make a 21 millimeter redshift map. Okay. Here is another telescope that we've been deploying. This is a telescope of the same size as what Haslam used. Haslam used the Atlasberg 100 meter. This is the Orbit Bird 100 meter telescope. It's the same size telescope as what was used 40 years ago. And I think there's nothing fundamentally different other than the way we took and analyzed data. So if you again make a map, so we write from modest, Haslam took the map of the whole sky, we meaning sitting over there, took a piece of sky. This is of 2 panels, 2 degrees each, so the bottom to up. So the whole panel is about 24 degrees wide, so two strips along the same declination. And we picked a convenient area in the sky where there happened to be an optical redshift survey. And at the bottom you can see the density of optical galaxies in this field when convolved to the resolution of the radio telescope beam. So you don't see anything, thousands of galaxies in this image, but they're all kind of smeared out because you don't have a lot of resolution. Now what you see in the radio image is coherent structure across frequencies. This is just a little slice through this previous map we saw. And now you see the single one emission which is smooth in frequency. A couple of gaps, like there's a cell phone band, there's TV over here, and apart from other very local foregrounds, you see mostly the synchrotron structure. And the idea is, you just have to come up with some way of modeling this out. If you have a way of subtracting this gigantic foreground, then you get to the border plot. So then you subtract it off, and then you see nothing, and you blow up the scale by a factor of 100, and then you start seeing a random structure at redshifts of about between 0.7 and 1.1. Statistically, you can ask, are these two maps statistically similar? And the answer is yes. The cross-correlation function of these two maps it has a positive signal, and there is only a single free parameter in this plot, which is the amplitude of the black line, which is related to, conveniently, it depends on the neutral amount of neutral 21 meter gas at that redshift, which is actually not known, and it's not known to better than a factor of 3 at redshift 1. Also depends on relative biases and other things about galaxies that's off the board, there's a B in here somewhere and an R. But so the thing we measured is a correlation in microkelvins, and you can convert it in omega H1 if you knew all the other things like bias and other things perfectly. But the statistical error you can see is now reasonably modestly under control, and you can actually make mapping, and this turns out to be in a plausible range of what the hydrogen content might be at redshift 1. So we think we now have the first demonstration that you can actually map this unresolved 21 centimeter emission at high redshift to see things. This is based on about 20 hours of green-back telescope time, and we saw the first demonstration of distant intensity mapping. And as that, we actually not setting any records for individual redshift of individual galaxies. We see no individual galaxy at all. That's fine. In fact, there's so many galaxies per beam, it wouldn't be meaningful to talk about individual galaxies. There's so many galaxies in each evolution element. So since then, they've allocated us 300 more hours to continue the survey and measure the order collision power spectrum and hopefully redshift space distortions, which you could use. Anyways, you can do various things with galaxy power spectra at high redshift. And that leads us to think about the next step. So we're starting to think, we're starting to get on a stepping stone to go to more and more ambitious ways of mapping to higher redshift. So right now there are a couple of experiments being thought about to map the whole sky out to some modest redshift to 2. Why stop at 1 square degree to all 20,000 square degrees out there? And it's a matter of surveying faster. And obviously, to do it faster, you want it not just a single pixel, but this is all done with 1 pixel. And nowadays, it's just not fashionable to have a single pixel anymore, since each pixel isn't all that expensive. And each pixel is like a cell phone receiver, which costs $1. Might as well have a few more of them. So, I mean, the dominant cost is not the receiver, dominant cost is processing the signal, but this is still cheap for 1 pixel. So you can still afford that many pixels. So there's nothing fundamentally preventing you from scanning the whole sky in a modest amount of time. And there have been various proposals, including cylinders and others, to map this out at various redshifts, initiatives from various collaborations. So one of these is a prototype that Jeff Peterson built. It's 2 cylinders. One way of doing it is you have, since the Earth is moving on you, and you're going to map the whole sky anyways, you might get away with no moving parts, and you might be able to do this quickly. Yes, the kind of volume you can do a survey. There's a couple of these things under study, including the Canadian one called Shine. Albert here is in a Fermilab initiative called CITA, and also an initiative by the NWA group called CARPET, various hopes of exploiting this technique to directly map high redshift with a modest investment in infrastructure. So, what's my conclusion about how futuristic and how far are we getting towards the zone of mapping, this infinite information and wonderful of our universe? I think there are a couple of things. One is that there hasn't been much progress. So this Haslam mapping 40 years ago, the telescopes haven't really fundamentally changed since then. We still same like same 1 pixel still. So you think there's been a missed opportunity of using Moore's law. You can have instead of 1 detector, but after 30 years, 1 detector means you now have a million detectors or something over Moore's law over 40 years. There's some huge number of increase in information you can process. And in the intensity mapping mode, the collecting area is already sufficient that we have. We just have to make the survey pretty faster. And now we've been getting into the regime of showing that you can actually process the foregrounds, that they are actually surmountable. And that's why we've been pushing to go the next step and have larger and dedicated surveys to really start digging into this huge amount of information. Thank you.